So let us start. So we are going to discuss the central forces. So central forces we mean, suppose if a planet is moving in an elliptical orbit, then actually, so this is the major axis and this is the minor axis, and in this actually there are two different focuses, and these focus, let us say this is C1 and this is C2. Then let us say the sun is located at this location and the planet is rotating around the sun like this, and there will be always an attractive force between these two and is always directed towards the sun. Suppose if the planet is located at this location, the force of attraction will be in this direction, and if the planet is located at this location and the force of direction is towards this particular sun. Now whatever may be the location of the position of this planet, the force is always directed towards the sun, and this nature of force we call as the central force. So here the central force we mean the line of action of the force is always directed towards its fixed point called as a pole. So this is what in polar form is called as a pole. So a central force by definition if the line of action of the force is always directed towards a fixed point, then the force is called as a central force. So this is called as a central force. So there is a specific importance for this kind of force. Why? Because the direction of the acceleration and the direction of the force are actually one and the same always, except for the definition that F is equal to ma, where the acceleration vector is getting multiplied with a scalar quantity called m, which is the mass. Then so the direction of the force and the direction of the acceleration are always the same. This is the fundamental rule. Now, why we discuss the central acceleration as a separate topic itself is, there is no transverse acceleration in this case. If there is no transverse acceleration, it will get certain fundamental properties, which are the basic rules of the planets, so how they are going to rotate around the sun. So, those rules actually, the angular momentum is going to be a constant, and the planet will always rotate in a plane, and all the basics of or whatever the required conditions of the Kepler's laws are derived from the central force equation, where every planet actually tries to obey the law of inverse square law. So this is what is called the inverse square law. As per Newton's law, what it says is, so the force between any two different masses is equal to g times of m1 m2 by r square. If you notice here, F is directly proportional to 1 by r square, and this is one particular case of the central force. So the central force has got certain fundamental importances. So those importances actually we are going to discuss it. Got it? So first you note down the definition of this central force, then actually we are going to analyze this case. A circular motion is also one case of central force, where the line of action of the centripetal force is always directed towards the center of the circle. So that is also one kind of central force. So the condition for the central force is the line of action has to be passing through a single point. That is the condition. Now all these derivations are actually coming from the fundamental principle what I have derived already in case of dynamics, right? So there is the transverse acceleration and the radial acceleration we have derived. So this is d square r by dt square minus r into d theta by dt whole square, and this is the radial component of acceleration r cap plus r into d square theta by dt square plus 2 times of dr by dt into d theta by dt into theta cap. So this is actually the transverse and the radial component of acceleration for any particle which is moving in a plane. Now, if the particle is moving in a plane and there actually, if the line of action is always directed towards a single point, then actually this is the line of action of the force. And if you notice, this is actually, this being the pole, the radial vector is this one. So this is the radial vector or the radius vector. And the radius vector, if you notice, the line of action of the force is negative direction of the radius vector. And this is r cap direction or the minus r cap direction to be specific. And there is no transverse acceleration. So this acceleration is not there. So no transverse acceleration is not there. So hence actually the line of action of the force is always towards the central acceleration. No transverse component of acceleration. Now from this relation of the planar motion, so this point actually is going to be 0 and this will always be there. And this acceleration we usually call as minus p, because this radial acceleration is always directed towards the center, which is the negative direction of the radius. Got it? Understood or not? So these are the specific conditions of the central force. Now actually these conditions actually will drive us to two different important conclusions. One is the angular momentum of a particle moving under central acceleration is always a constant. So this is one important conclusion. And the second important conclusion is the path of the particle will always be a planar. Or no three-dimensional motion is possible. In case of central force. So these are the two important conclusions of the central force. So the angular momentum is going to be a constant value. That is one important conclusion. And the second important conclusion is the particle can travel only in a plane, which essentially means that, so suppose if the planet, let us say Earth is trying to move around the sun like this. So if the Earth is trying to move around the sun, then actually being this is one of the focus of the ellipse which where the sun is located, then the particle which is the Earth here will try to rotate in an elliptical orbit like this. But it cannot go an elliptical orbit like this and one more time actually like this and one more time like this. So it cannot keep on going in this manner. So it has to travel only in a plane. So the plane has to be fixed. So the plane may be vertical or the plane may be slant or the plane may be horizontal. But once it fixes, right, so that path will be there throughout the life of the planet. So Earth being rotating around the sun in an elliptical orbit, so this fixed orbit is always be there. And it cannot move out of the planet or it won't change the path of the planet. Got it? So this will always tries to rotate in an elliptical orbit, which is a plane. Now actually we are going to derive the conclusions, so which we have discussed it here mathematically. Got it? You can note down this. Done? Are you done? Now see this. So based on this understanding, so the transverse component of acceleration is going to be 0. Hence, there is only one radial acceleration which is directed towards the pole where the sun is located. So from this relation, r square d square theta by dt square plus 2 times of dr by dt into d theta by dt. So this value is being 0, and this can be expressed as, so this is r square d theta by dt d by dt of, so now if you take the derivative of this, see this, if I expand this derivative, then actually if I multiply it 1 by r, so 1 by r times of, so this is r square into d square theta by dt square plus d theta by dt into 2r into dr by dt. Now if I take this 1 by r inside, then actually, so this is going to be this is r into d square theta by dt square plus 2 times of dr by dt into d theta by dt. Now if you notice, this is exactly what it is, the transverse component of acceleration. Now this transverse component of acceleration can be expressed in a different manner, 1 by r times of d by dt times of r square d theta by dt. So this transverse component now actually I have expressed in this particular format, and this component is anyway known for any central force. Then actually taking this exact differential, if you integrate it, so d by dt of r square d theta by dt is equal to integral 0. So if you take this dt to this side, so this is down. Now this d and integral will cancel out, and r square d theta by dt is equal to constant. Let us say this constant is h. So this is one very, very important conclusion here. And left side actually, if you notice, this is the expression of the angular momentum. So angular momentum by definition, so if a particle is moving in any path randomly, let us say the particle is trying to move in this particular path, then the angular momentum will be r cross mv. So this is the angular momentum by definition. So r cross mv is the angular momentum. Now here, for any circular path, if you notice, this r and v are always perpendicular to each other. Hence, this cross can be replaced with sin 90. Then r into m into v. So this is mvr. So mvr is the angular momentum. Now this angular momentum per unit mass, if you take it, so this is going to be v into r. Now here, this one whatever we have got is nothing but, so this is r times of r d theta by dt. So r d theta by dt is nothing but the peripheral velocity. D theta by dt is the angular velocity. So this is r times of omega. So r omega multiplied by r, which is nothing but the angular momentum. So this angular momentum is coming out to be a constant from the definition of central force, which essentially indirectly says that the transverse acceleration is 0, which concludes that the angular momentum is constant. Got it? So this is one very, very important conclusion. And as per the Kepler's second law, what it says is the aerial velocity is always a constant. So that is from the conclusion of angular momentum, which is going to be a constant. So from this relation, Kepler's second law comes out. Got it? You can note down this. So this is one conclusion, and the second one is, so it always rotates in a plane. So that is the second conclusion. Why it always tries to rotate in a plane is, now actually we know that, so the radius direction is going away from the pole. Let us say this is the radius direction. So let us say this is O and this is P. So OP is the radius vector. Let OP be the radius vector, and we know that d square r by dt square vector. So OP, so this is the radius vector. Let us say this is r bar. Now d square r by dt square is nothing but the acceleration vector, and this acceleration vector is always anti-parallel to the radius vector. Why it is always anti-parallel to the radius vector is in case of central force. Why? Because d square r by dt square is nothing but the acceleration vector, and the acceleration vector and the force vector are always the same direction. Now in case of central force, we explicitly says that actually this is always in the direction of the so towards the pole or towards the center. So this is the direction of the acceleration because this is the central force or the centripetal force. Now here actually this is the radius vector and this is the force vector, which is the attractive force towards the sun. So this vector is nothing but the force vector, which is always the vector of the acceleration. As there is no transverse acceleration, there is only the radial component of the acceleration. That radial component of acceleration in the negative direction of r. So these two are always anti-parallel to each other. So r cross d square r by dt square is always equal to 0. This is one important conclusion. So because this is happening only just because of the reason that this is a central force, which essentially means that no transverse acceleration. So r cross dr by dt, one and the other are anti-parallel to each other. Hence the cross product is going to be 0. Now for this actually what I will do is I will add dr by dt cross dr by dt. So by adding a 0, so dr by dt cross dr by dt is anyway 0 because both the vectors are one and the same. So I can write as if like adding a 0 here, dr by dt cross dr by dt equal to 0, and this can be called as d by dt of r cross dr by dt. So this is d by dt of r cross dr by dt. So this is r cross d square r by dt square plus dr by dt cross dr by dt. So these are one and the same. Now from this relation, if I take this dt to the other side and then try to integrate on either side, this is being an exact differential. So r cross dr by dt is going to be a constant. R cross dr by dt is going to be a constant. So, and this is a constant and it is a vector. Hence this is a constant vector. So this is a constant vector. Now from this constant vector, if I take r dot on either sides, so this is r dot r cross dr by dt. So r dot r cross dr by dt is always 0. Why? Because this is a scalar triple product where there are two different equal vectors. So r dot r cross dr by dt, which says that this is ideally 0 always because this is a scalar triple product with two equal vectors. So if this is 0, then r dot c has to be 0. And c is a constant vector. So r dot c is always a constant. So r dot c is always 0. Hence r and c are always perpendicular to each other. So r and c are always perpendicular to each other. So if these two are perpendicular to each other, what it essentially conveys for us is C is a constant vector. Let us say this is my hand which represents a constant vector always. I need to draw a radial vector which is always perpendicular to this, which essentially means that I can draw a vector like this, I can draw a vector like this, I can draw a vector like this, and I can draw a vector like this. So it is always perpendicular to my hand, and this hand is nothing but the C vector, which is a constant vector. So if this is the constant vector, then the radial vector has to be always perpendicular to each other, and that is always possible only if I draw the vector in the plane joining this area. So this is the area. So this is nothing but the planar area. Suppose actually if I stand, let us say myself actually I am standing on the ground, so myself represents the vector C, then the place where I stand, which is the plane surface, that surface is the only possible option for me to draw a vector which is perpendicular to myself. So that plane is nothing but the r directional vector, which is the radial vector. Suppose if I take my feet as the pole, then from the pole actually I can draw any vector on the ground, and that vector will always be on the plane of the ground. So I can draw only a coplanar vector there. So it essentially means for us is this radial vector which represents the path of the particle. This path is possible only on the plane. From this conclusion of r perpendicular to C, because r has to be perpendicular to a vector which is a constant vector. So let us say if this is the constant vector which represents the chalk piece direction is the constant vector, the possible option of r is only this one. So all these are the possible options of the radius vector. So the path of the particle is only on the plane joining this particular shape. So any planar surface can be a possible option for us based on this conclusion in case of the central force. So this derivation we have made from the assumption of the central force, assuming that the radial direction of component of, so assuming that the force is always directed towards the pole, and one more important assumption is the transverse component of acceleration is 0. With these two assumptions we concluded this. Got it? So this is the Kepler's first law. So angular momentum is constant. From there actually we are going to derive the Kepler's second law, and the first law is every planet tries to rotate in an elliptical orbit with sun as one of the focus. So the partial conclusion is made from this understanding of r perpendicular to C, which says that a planar surface, that planar in this particular case of the central force, which is proportional to P is inversely proportional to 1 by r square, then it is going to be ellipse. Got it? So that is the partial conclusion we have made from this understanding of r perpendicular to C. Got it? Any questions on this? Okay. So in case of central forces, the sectorial area is going to be a constant. So that we are going to prove that now. So the sectorial area, rate of sectorial area is always constant in case of central force. What it essentially means for us is, let us say this is one radial vector. Let us say this is one radial vector, and this is another radial vector which is separated by an angle of delta theta, and let us say this is the r vector, and from this r actually after moving for a elemental time of delta t, let us say this is the difference radial vector r plus delta r, let us say. So this is moving from a location of r to r plus delta r in a time of delta t for an angle of delta theta. So with this understanding, the area that is going to be covered by these two radial vectors, this is the vector. So I will just draw it here. This is the pole, and this is one radial vector. This is another radial vector. And then So this is delta theta, and this length, so this is delta r, and this is r plus delta r. So the length of this is r plus delta r, and the length of this is r. Now the angle between these two is delta theta. I have drawn a bigger length, but actually this was covered within a smaller time of delta t equal to almost tending to 0. So this is as if like this, and then from this understanding, the area that it is going to be covered within the time of delta t, which is almost tending to 0, is going to be, so you can approximate this as if like it is a triangle. Why? Because the time what we have considered it is delta t tending to 0. That means very next moment we mean the vector that is started from here, and within very next moment, this is the vector we can think of immediately. That means this delta theta tending to 0, as delta t tending to 0, and delta r also will be tending to 0, as everything is interrelated to each other. From this understanding, the area of the triangle is going to be the area of the triangle, or the approximated triangle, covered by that planet within the elemental time of delta t tending to 0 is delta A is equal to, so for any triangle with length of r and r plus delta r, the area is going to be half r into r plus delta r into sine of angle between these two. So for any triangle you can think of, let us say if this angle is theta and this is A and this is B, then the area of this triangle is half AB sine theta. So same formula I have used by an approximated triangle which is going to be covered by these two radius vector within a small time of delta t. So here if I take the rate of area covered, delta A by delta t, delta A by delta t is equal to half of r into r plus delta r into sine of delta theta by delta t. So if I take limit delta tending to 0, limit delta t tending to 0, delta A by delta t is equal to half of r into r plus delta r into sine of delta theta by delta theta into delta theta by delta t. So I have multiplied and divided with delta theta. So from there, as delta t tending to 0, so delta theta also will tend to 0 and delta r also will tend to 0. So if this is the understanding, then sine delta theta by delta theta, as delta theta tending to 0, this can be replaced with 1. Hence, so sine theta by theta, limit theta tending to 0 is going to be 1. So that value if I replace it, and delta r also if I replace with 0, I left with 1 by 2 times of r square into d theta by dt. So this is what I left over for the expression of dA by dt, which is nothing but the rate of sectorial area. So the area that it is going to cover within a time of delta t. So that area rate is going to be given by 1 by 2 times of r square d theta by dt. Got it? And from the previous expression, I proved that r square into d theta by dt, which is the angular momentum, this angular momentum is going to be a constant which is equal to h. So here dA by dt is equal to 1 by 2 times of H. This is one important understanding of central force. Got it? Understood? Is this understood? Okay. So with this understanding, now let us say that simply dA by dt is going to be h by 2, where h is a constant. So which essentially means that the rate of sectorial area is going to be an important constant. dA by dt is equal to 1 by 2 times of r square into d theta by dt, where r square into d theta by dt you can replace with h, where h is the
constant.
Where h is the constant. Got it? So this is a h is a constant which we call as the angular momentum. So which essentially says that dA by dt equal to h by 2 is a constant. Now here what it means for us is, suppose if the planet is trying to rotate in an elliptical orbit like this, now this is being the focus. So this focus where the sun is located, and then the planet actually, let us say at one time this is located at this location, and after a moment, so the planet got shifted to this location. Now taking this sector, if I consider this area, and this, let us say to cover this area it took, let us say, 1 day. Now the equivalent area, which is nothing but the same magnitude of this area, is covered from this location to this location, let us say. So this is the sectorial area to cover from this place to this place. Now if you notice, it will take 1 day itself to cover from here to here. So this is again 1 day, but the distance that it is going to cover from here to here is very less, but the distance that it is going to cover from here to here is very high when compared to this one. This is one important fundamental property of any planet. So it will take the same time to cover less distance and to cover more distance here. So here it is the less distance, here it is the more distance. Why? Because the product of r into v is going to be a constant, which is the angular momentum. So that is r square into d theta by dt is nothing but r into r d theta by dt. So r d theta by dt is v, which is the peripheral velocity. This rv is going to be a constant. Because of this reason, more radius and less velocity, less radius, more velocity, because rv being constant, r is inversely proportional to the velocity. So more the radius, lesser the velocity. More the velocity, lesser the radius. So that is an important fundamental property of any planet here. Now what it means for us is, see this, it is taking this distance, right? Now here when it is trying to move from here to here, it took very less time. But actually here it took very high time. So 1 day itself, but very longer distance. So here actually for the rotation of the earth, it won't take any difference, because actually 1 day 24 hours always. But by the season wise there will be a difference. Why? Because so here actually within 1 day it is going to cover more distance and trying to go away from the sun. And indirectly we can explain the same way in a different manner. The centrifugal force is nothing but mv square by r, which is the centrifugal force. And this has to be balanced by the attraction towards the sun. The centrifugal force, what it says is mv square by r. So if the velocity is more, then the centrifugal force is more. Here actually if the planet is at this location, there actually the centrifugal force is trying to go away from the orbit. So this is mv square by r, and this value is more, because earth is trying to attract heavily because of the gravitational force of g into m1 m2 by r square, r being very less at this location. the force of attraction by the earth is very, very high. Hence, the planet has got only one option, that is, it has to increase its velocity so that its square of the velocity is going to be the centrifugal force, which will be balanced by the attractive force of the sun. Otherwise, actually, it will fall down into the sun. Suppose if we take the other side, here actually, if it tries to maintain the same velocity, then the centrifugal force is more at this location than the attractive force of the sun. Hence, in such cases, the possibility is the planet can go out of the orbit, because the centrifugal force is more, provided if it is not reducing its velocity. So, it will reduce its velocity so that it will compensate the central force of the sun. So, here the velocity is less, the centrifugal force is less, hence the centripetal force is also less, which is the attractive force of the sun, which is the central force in our case. And here the velocity is more, being the centrifugal force is more, and the centripetal force is also more. So one and the other actually is going to be balanced out, and that it is going to achieve by increasing its velocity here and by reducing its velocity here. So by reducing and increasing, it will try to maintain the angular momentum as a constant value. This is important conclusion. So that we can state as if like it is a statement, that is dA by dt is equal to constant, which is equal to h by 2, which is the angular momentum. Got it? So h is the angular momentum. So this is the Kepler's second law. We state that. So first law, first you note down this. I am going to write the Kepler's laws. Okay. So what Kepler's first law says is, every planet tries to rotate in an elliptical orbit with sun as one of its focus. So this is the first law. And the second law is, every planet swept equal areas by the radial vector from the sun to the planet in equal intervals of time. So this is the second law. And the third law says that t square by r cube is always a constant for any planet where t is the period of revolution and r is the length of the semi-major axis. Length of the semi-major axis. So these are the three important laws of Kepler. Got it? Okay, so you can note down this. Then, okay. So, the differential equation of any central orbit, we are going to derive that now. So, in case of central orbits, d square r by dt square minus r into d theta by dt whole square, which is the radial acceleration, and the magnitude of that is going to be minus p. So this minus sign represents that the centripetal acceleration is always directed towards the negative direction of r. Negative direction of radial vector. So this is the differential equation in terms of r and t, but actually it is more meaningful to express in terms of something called u, which is equal to 1 by r equal to u, or u is equal to 1 by r and theta. So with these two variables, the same differential equation can be expressed in a more convenient way, which is going to be used in any case of central orbits. Now we are going to do that. Now actually we got the fundamental relation r square into d theta by dt is equal to constant for any central orbit. So this is for any central orbit where h is the angular momentum. So, and here p is the central acceleration, centripetal acceleration, which we have noted down. Now from that relation, r is equal to 1 by u. So dr by dt is equal to minus 1 by u square into du by dt. So this is one relation. Now here dr by dt can be expressed as dr by d theta into d theta by dt. So this is how you can express it. Now here dr by d theta you can express as r is equal to 1 by u. It implies dr by d theta is equal to minus 1 by u square into du by d theta. So this is for dr by dt. Minus 1 by u square into du by d theta. Now if you take the derivative again so that you can calculate this one, d square r by dt square is equal to d by dt. So d by dt of dr by dt. This can be further expressed as d by d theta of dr by dt into d theta by dt. So this is actually the chain rule what I am using it here. So d by dt can be expressed as d by d theta into d theta by dt. So d theta and d theta coming together. So that it won't make any difference to our differential equation. Now here d by d theta of, so here dr by dt minus 1 by u square into du by d theta into d theta by dt. So dr by dt here actually, so dr by d theta into d theta by dt. So r equal to 1 by u. I think so. This is d theta by dt left over here. So d theta by dt is left over here. So r equal to 1 by u. So 1 by u, you can write that dr by d theta. So dr by dt sorry. So I'll do it now. See this, r equal to 1 by u. Now dr by dt, if you want to calculate, this is d by dt of r. So this can be further expressed as d by d theta into of r into d theta by dt. So this is based on the chain rule. Now here dr by d theta you can calculate as minus 1 by u square into du by d theta into d theta by dt. So minus 1 by u square into du by d theta into d theta by dt you can replace as h by r square. Or h u square, because u is equal to 1 by r we have introduced. So this can be replaced as h u square. So this u square cancel out, and minus h into du by d theta is the value of dr by dt. Minus h into du by d theta. Now from this relation, so if you take the derivative again, d square r by, so this is d square r by dt square. So d square r by dt square, d by dt times of dr by dt, and this can be further expressed as d by d theta of dr by dt into d theta by dt. The same procedure what I have adapted as a chain rule here as well. So dr by dt we have already calculated, that is minus h times of du by d theta into d theta by dt. So this is d by d theta minus h into d square u by d theta square into d theta by dt, and d theta by dt is h by r square, which is equal to h u square. So this is minus h square u square into d square u by d theta square. So this is the value of d square r by dt square. Now from this fundamental relation of the centripetal acceleration, we have calculated d square r by dt square is going to be equal to minus h square u square times of d square u by d theta square. So this, if you replace it here, and d theta by dt we have got h u square. If you replace, then we are going to arrive at the acceleration equation in case of the format of r equal to 1 by u. First you note down this, then we are going to substitute there, and then finally arrive at the differential equation of a central orbit. Got it? Done? Okay. Now this relation, if you put it there, so the expressions are what we are going to replace it here. It is, one is r you can replace as 1 by u, and another is d theta by dt you can replace as h u square, and another is d square r by dt square you can replace as minus h square u square into d square u by d theta square. Now if you replace it there, minus h square u square into d square u by d theta square minus r into, r meaning 1 by u, and d theta by dt is h into u square whole square is equal to minus p, where p is the central acceleration. This minus and this minus will cancel out, and then h square u square if you take out, then d square u by d theta square plus h square goes out and u square also goes out. U square by u is u is equal to p, or to be specific, d square u by d theta square plus u is equal to p by h square u square is the differential equation of a central orbit. So this is the differential equation of any central orbit. Got it? So this is the fundamental relation for any central orbit where u is going to be 1 by r and p is the centripetal acceleration and h is the angular momentum and theta is the variable which is the path variable. So r and theta are the fundamental relations which will describe the path of the particle, or in this case is the path of the planet. So for any central force, this is the differential equation. So this is irrespective of the law of force, where the law of force can be inverse square law or inverse cube law or whatever may be the law. So irrespective of that, this is the path of the central orbit from the fundamental condition of the force is always directed towards the pole and there is no transverse acceleration. That kind of case we call as the central force. For that central force, this has to be the path of the particle. Got it? Understood? Do you have any questions on this? Any questions on this? Okay, great. So with this, I would like to stop the class for today. So tomorrow, actually, based on this understanding, for certain cases, actually, we are going to discuss the path of the particles under the law of forces. Got it? Okay, yeah. So that's all for today. Thank you. Good night.